So back to our original question. So if you ask now to determine whether there exists a route from city A to city F, I've just added another node from that in that question so that things might be interesting. So now, how are you going to achieve that? Remember, elements in a graph are not always arranged in any order. As you can see, it's just like a drawing. And then now we already know, now using either a matrix or an adjacency list, now we get an order through which elements are stored. Now, how are we going to move between these elements in the best way in order to achieve our greatest results? Now, there are two common ways, and maybe we draw something. One of them is using the breadth first traversal, or what is it called? The other one is called the depth first traversal. So we're going to start with the easy one. So a depth first traversal. So maybe from Wikipedia, what is a depth first traversal? I mean, from the word depth, I always say that using the depth first traversal, we are just trying to see how deep a node is connected to other nodes. Like if we begin with the node A, we will go deep to the last node that is has a connection to node A before we move to any other node. So this is what, this is not Wikipedia but tutorials point. No good definition. So we're not going to waste time with definitions. So, for example, if maybe we were trying to explore a depth first traversal, this is what we would have done. First of all, we will check if node A is connected to node B, and then if they are, then we move to B. Again, we check if node B is connected to node C. If it is, we continue this direction until we can't go any further. I mean, you see, we can't go past that. That's now when we choose to move the other direction. So we check again now if C is connected to D, we continue moving this way. We again check if D is connected to I. So the process moves on this way until we can't go any much further down or side. So this is the depth first traversal. The things you should remember in order for us to achieve that, this a stack is used. So maybe we can see it practically how it operates. Maybe I'll just write something here. Depth first traversal. Maybe we can just see how we can traverse this graph using the depth first traversal. So this is our graph, and so to perform our traversal, first of all, we will need a graph. We will also need the graph will store the nodes. Yeah, so we will need a graph, then a node, and then a new file because we've added another node. So very first we're going to clean up our code. Just create some packages. The first package will be the models package, and in the models package we will have our graph and the node. So create a graph class. And also we create a node class. So our node will have a name, so it will be a private char name. And also it will have a list of its neighbors, I mean the nodes that are related to this node. So it will be a list type node. We will call it neighbors. And then to import this. So we need a constructor to initialize our node. It will be a public node. It will take in a character, which is the name of the node. So char name. And now that name will be equivalent to the node's name. So we are going to assign it the thing that has been passed. Then also we will also decide now that our list will be our an array list. So we're going to create a method to add a node to the list. Add neighbor. And this method will also take in a node, the node that is related to this node. So what we're going to do, we're just going to add the node in the list. What else do we need? We need some getters. Some getters. So we're going to get the name and the list of the neighbor. List. I believe we are done. That's so inside our graph now. Our graph will have an array of nodes. Yeah, and provide done. Yeah, and what do we need? We need a constructor also to initialize a node, not a node, but the graph, public graph. And now this will take in the number of nodes in the graph. So int number. So each time we initialize a graph, we have to tell it that you are supposed to be having this number of nodes. Maybe we just create a data public get nodes. Yeah, and we're done. So get nodes. So we're done. So what again should we create now? We need a file to read data from. So this file we're going to call it traversal. And the first line will be the number of rows in the matrix, columns, and then now we need the name of the node. So we're going to just type the names A, B, C, E, E, F. It was the last, and then I'm just going to copy what we had written here. And paste it to the new file. So since we've added another node, we're going to add some information. And the last line will 1, 2, 3, 4, 5, 6. I also eliminated this and added something here 2600. Eliminated this. So now let's just create another package. Now this package will contain the traversals. Yeah, traversals. And our first traversal will be the depth first traversal. Now we need a main method to execute the traversal. And as usual, we are going to read data from the file. So it's good if we initialize a file known as traversal. And the file. Now let's just use some try catch blocks. We need to catch the file not found exemption. So let's catch the IOE exemption because we're going to use other input and output classes. So it's good if we catch the input output exemption in general. So as usual, we print it to the console a.get message, and then now we first of all need to check if the file exists. Oh, if the file exists, what are we supposed to do? We are supposed to read it. So we initialize a file reader. File reader. Just call it reader. Reader, and it's supposed to read our current file. Now, since now the file reader reads contents in bytes, we don't want to read contents in bytes, so we're just going to use now a buffered reader to now read the actual contents of the file. So it's a new buffered reader, and it will read file from the reader. We already know that the first line represents the number of rows in the matrix. So maybe we initialize the rows as an integer, and we need to read the whole line because it's only a single thing. So again, remember buffer.read line, it returns a string and we need it as an integer. So we're just going very fast to convert the string into an integer. Now here we are reading the first line in the file. Okay. Now we need to read the second line, which we are told represents the columns of the matrix. So again, very fast, this line again is going to read the second line of the file. Okay. Now the following line represents the name of the node. So maybe first of all we need to initialize our graph and tell it. So we initialize our graph. So graph will be equivalent to a new graph. How many? We need the number of nodes that is supposed to have. It will be equivalent to the number of rows in our matrix and columns. So maybe initializing a. Did you create a method to add the nodes in the graph? Let me just check. We're getting the nodes, but we are not. So maybe. Let's just think this through. Maybe we should pass in the node. We should just pass in them nodes, and then we we return the nodes. Something of this kind, and then here we're not going to initialize our graph here. Here we're going to initialize now the node array. Yeah, the node array. So node array nodes is equivalent to a new node array. Its size should be, then let's add content in the array. So we're going to create a loop that executes how many times? 6 times in order for us to read the names of the nodes. And then each time we read the name, we create a node and then assign it that name. So it should be less than rows. Yeah, so and then now read the line. We already know it returns a string. So buffer dot read line. Now we need it in character form. Remember, our node is supposed to have a character name. So what you're going to do, you're going to convert the string into a character. Node name is equivalent to name dot char at 0. We already know it's one element. Yeah. So now we initialize our node as node equals to a new node, and then we assign it that name, node name. So in the first iteration we will get a, and then a will be converted to a character, and then now we create a node and then assign it a, and then we store that node inside our node array is equals to node. Yeah. So we already know that. What's up? Now we will read them. Maybe we can just read them for fun. So out nodes at I dot get name. Yeah, and then to make things funny, I will just do something. Maybe let's try and see what happens. So we already have our nodes stored in the matrix. We have node 0, node A is equivalent to index 0, and then node B is at index 1, node C is at index 2, and so forth and so on. So what now we need to do is we need to initialize a graph. Yeah, and so our graph will be, we'll just call it graph. And you remember, our graph takes in the node. It's a new graph. Forgive my Kotlin. So it's a new graph. Yeah, and it takes in what does it do? It takes in a node array in its constructor. So we're just going to pass it with the nodes that we've created. And then now we need now to see the relationship between the nodes. You remember the elements of the matrix give us the relationship between the nodes. So it can be anything, actually, not the relationship alone. You can be told that the matrix now gives you maybe the weight. Now in our case, remember it was the distance. So what are we supposed to do? Since we are reading elements in a matrix, we're going to initialize now our matrix. And for simplicity, buffer.read line gives us a string, and that's the method that we want to stick to. So we are going to initialize it as a string matrix. So we have now a string matrix will be equivalent to a new string matrix, which will take in the number of rows that we have and the number of columns. Yeah, now as usual, we want things made easier. So we are going to create a loop that executes 6 times, or the number of rows that we have. First, let's do that. So we are going to initialize a loop that reads the number of rows that we have. The number of rows, and then maybe we can just read the row and see. So string row will be equivalent to now buffer dot read line, and maybe we can just see how it looks. So let's see how our row looks like, and then now after reading now the row, we need to get each and the elements in the columns now, so that now we can see the relationships. So as it runs, we are going now to execute another loop. Let's just see. Yeah, so now you can see we have our rows. This is row 1. Maybe you can just write something for clarity purposes. Yeah, so we are going to write row, and then add the index that we're at, and then we just put a good arrow, then we can run it. Now as it runs, we are going now to create that loop that gets the elements in the columns. Yeah, now this loop will be the size of the row. Yeah, now you can see row 0, we have 0, blah, 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 which is what we have in our matrix. Yeah, now let's get the elements in the row. So first of all, we don't want to get the empty spaces, because if we use the chart.at, we will chart, this position will be an empty space, and we don't need empty spaces. So what are we supposed to do? We can create the string into an array by splitting it using the empty spaces. Yeah, and then now since it's a string array, we have to tell Java that it's an array. Now this will be indexed at I believe so. Let's just give it test one. And then now j now will be less than dot length, I believe. Yeah, illegal start expression 42. I hadn't completed that, so maybe now we can now print out and see the element in row I, but at position j. Yeah, no, so we will just print out the element in row I, which in the first iteration will be row 0, and then we check its content. Yeah, so maybe we call it to string, I believe so. It's not an array. No. What am I doing? God damn it. No, we initialized our matrix. Maybe this is the best place that we can now store the elements in the matrix now, you see. So our matrix at column at row I and then position j will be equivalent to the row at j. So let me just eliminate but for clarity purposes. And then maybe what we need to see is the element at row J first of all. Let's let's just see what it is. What it is? Because I think there's a goat that is making me mad outside here. So maybe we just put a knife on its neck. And, yeah, you can see we've gotten so many zeros, but not so many zeros. We believe this is the F section that has so many zeros. So you can see that's the, that's our J. Now maybe since we can get all the elements in the matrix, maybe we need just to say something. See, you see, remember row 0 is node A and column 0 is also node A. So we are going to check the relationship between row 0 and column 0, which will be equivalent to node 0 and node 0. If we have something, it means there exists a root from node 0 to 0. And I believe there's an error. This is not what A, B, C, D. Is there a way between D to A? Let me just check. D to A at 3000. It's there. So my bad, my bad. Yeah, so we, maybe we just write something not to get confused. Remember, graph dot get nodes dot I. This will be our current node, the node that we are at. Maybe I just call it node current, and then now the column will give us the node that we column node is equals to graph dot get nodes at A. Now these are the nodes that we will be comparing. Now if row J, or maybe let me use the matrix, this will be the best. Control C. Now if the matrix, the element in the matrix, it's a string, so equals 0, it means there is no relationship, but we need the relationship. So let's just negate this. So if it's not equal to 0, then it means there is a relationship. So what we're going to do, we're going to grab the current node and then give it a neighbor. So dot add neighbor, the column node now. Up and then do like that, and I believe we are done. So maybe what you're supposed to do right now is check the neighbors of the nodes. So printing, maybe let's just say printing neighbors, or should we create a method that does that for good programming practices? Maybe we just do it manually. So we just get our current node. So we're just going to use graph.get nodes and then dot size dot length. It was an array, I believe. So in each node, we're just going to print out. Maybe let's just get the current node. Maybe I'll just use this. So the current node, what should we print? Dot get neighbors. It's a list. Let's just print it out as that before we loop through the neighbors and print them one by one, because I know we're going to get some node. Yeah, so we have this node, this node, this. So F doesn't have neighbors, so you can see it doesn't have anything. So maybe we can loop through the list again. Parent dot get neighbors dot size, I believe. Yeah. Then now we get the neighbor. No, I'll just type it manually. Node neighbor will be equivalent to parent dot get neighbors, and then dot get j, and then maybe we can print that out and see it. So we are going to print. Well, let's just write something. So it will be parent plus current dot get name dot. I will just write it here. So plus j plus on. Maybe I just put this in a bracket because I don't want 0. Just want node 1. Yeah, put that in a bracket, and then plus neighbor plus. I'll just tell you what I'm doing. Plus neighbor now. I just want to say the current node, which will be node blah. The first neighbor, I've added 1 because j is 0, and I don't want to say 0 neighbor. The first neighbor, I just add about second. No. Neighbor will be that one. So let's just see. So current was A, which was A1, A, and neighbor 1. We need to do something more. So this was get name, and then I'll add this. I'll just put it here. So plus neighbor 1 plus this thing equals to neighbor dot get name. Yeah, now we will know that. Yeah, so we can see A neighbors C, A neighbors D, B neighbors C, C neighbors B, C neighbors D. Maybe we can just compare it to our file. So yeah, so we can see neighbor A neighbor C, yeah, A neighbor C, A neighbors B, A neighbors D, B neighbors C, B neighbors C, and then C neighbors D, and then C neighbors E, and then D neighbors A, and then D neighbors C, and then E neighbors C. F doesn't neighbor. anyone, so that's why it's not printed out. So we have our graph ready. So I believe it's time we perform our depth first traversal to see how we can move through all the nodes without leaving out any of each node. You see, from here in our loop, when we said current dot get neighbors, since f didn't have any neighbors, we didn't print it out. So we need a way through which we can see all the nodes whether they have neighbors or not. So we are just going to create another method for simplicity purposes. So we are going to initiate a public static because you're going to read it from the main method. It will be static, and it's not going to return anything. We're just going to print things on the console. So a depth first, and it will take in a graph, and then we'll also give it the start node so that we can see traversing through the graph starting from different nodes. So things you should remember. In order for us to achieve a depth first traversal, a stack is used to store and monitor the nodes. And from your basic data structures, a stack employs an architecture known as LIFO. I mean, the last element to enter the stack is the first to be retrieved. So maybe let's just write some code. You'll understand it later. If you don't know about stacks, you can just Google them first and understand them. So we're going to initialize our stack. We initialize our stack. So stack is equals to a new stack. We won't provide the size. We need to indicate maybe the type that it will carry, so it requires some generics. So node, what is this saying? So now we add our start node. We add our start node to the stack. The stack, so it will be simple as stack dot add node. Then now, for us to achieve the traversal we create a condition that will perform the traversal for us. So now while the stack is not empty, remember we've added the the first node, so we'll just negate that. So while the stack is not empty, we will first of all get the current node. So current node is equals to, we just remove the topmost element. So it will be stack dot pop, I believe. Now from the documentation, let's just see the documentation very fast. The pop method, you see, removes the object at the top of this stack and returns that object. So if we use this pop method, we are going to get the topmost element in the stack, and then we store it in the variable current. So maybe we can just print out the current node, current dot name. And then now, since we are moving inside the node, we have to get its neighbors. So again, we will create a loop that gets the neighbors of the node, current node, then dot get neighbors, and then dot size. So if it has a neighbor, let's just say an example, what will happen? We will maybe, let's say we are starting with node A. We add it into the stack, and then now we print A, and then now we get its neighbors, which will be C and D. So node neighbor is equivalent to current dot get neighbors dot get I. So this is the neighbor, the first neighbor maybe is C. We get C, and then we push it in the stack. Dot push is push. That's how we add the neighbor. So let's say it pushes C and D, and then now let's just run it and see what happens. So before we explain anything. So this is the depth first traversal. This is the condition that performs the traversal. So maybe from our main method where we have the graph, we can we can just comment out the SO outs we made for things to be good. And then now we just call the depth first traversal here, depth first, and then we provide the graph, and then the first node. So maybe we can see what happens. Yeah, forgive my C shape, I should have used a small d, but maybe we can just change it as it runs. Something wrong has happened. Okay, now I understand why it's executing. The stack is not going to be empty. You see, we have different types of graphs. Maybe that's a thing that I should have mentioned earlier, but I knew it would come up. So maybe we should write something. We have different types of graphs. We have maybe one, we have connected graphs. We have connected. We have disconnected. Disconnected. We have like in our example, we have those graphs that are unidirectional. I mean, you only have one way from this node to this, which they're usually indicated with an arrow. You see, in our case, now the graph is bidirectional. I mean, you can go from A to C and from C to A. Now, when we take the first node to be A and then add its neighbors, and then now you see now in the second iteration, the next node will be maybe C. We take its neighbors. We will also take D, which has already been taken, and E, and then we add it in the stack again. Now you see, we will always be in an infinite loop in somewhere like this. So we need a condition that tells us that you have already moved through node A, because if we come to C, C will also add A to the stack, and then we will begin again the process again and again and again. We add again C, we add again D. So maybe let's see another example, a good example that performs the traversal.